So my flux limiter is a switch. Basically, let's say we have a UI. I'm not going to write the UI bar because like in finite volume, everything is all the UIs are actually cell averages, and the UI minus 1 and the UI plus 1. So these are cell averages. So what I want to make sure is that my reconstruction, no matter what, is not going to exceed the local. It's not going to exceed the maximum of any cell averages, right? So basically, what I want to do is I want to reconstruct the slope in this cell. So I want to get a slope in this cell so that the maximum of that slope is not going to exceed the value here, and the minimum of the slope is not going to dip below the value on the left. Okay, so how do I reconstruct the slope? So the slope at the ith cell, okay, it is equal to, if I'm in a continuous region, the slope should be equal to ui minus 1 divided by delta x. In continuous region, it should be equal to 0 if ui is a local maximum. So if it's if continuous, and this is if ui is local maximum. Okay, so this is a slope I use to extrapolate towards the right. So maybe I should say ui slope I to I plus half. That's kind of the slope between between the cell center I and I plus half. All right. Okay. And what I mean by if continuous is that so I should modify this region by saying if ui plus 1 minus ui is equal to ui minus 1. Well, this is basically a linear region. If ui is sitting between two cells and ui is exactly the average of its left value and right value, then I'm very comfortable in doing the extrapolation. Okay. And this, if ui is a local maximum or minimum, means if ui plus 1 minus ui has opposite sign as ui minus 1. All right, these are two extreme cases. One extreme case is that the two deltas are of the same sign and exactly equal, has the same slope. The other extreme case is if the two deltas has the opposite sign, they are not even the same sign. So we know these two extreme cases. In one case we are doing extrapolation, the other case we are doing piecewise constant. Now the question is, what do we do in the middle? Okay, what do we do in the middle is the job of a limiter. So the slope of I to I plus half is going to be equal to ui minus 1 over delta x times the limiter. Limiter I call phi. You're going to see the limiter is a nonlinear function. And the limiter phi is going to depend on the ratio of this value and this value. All right, it's going to depend on the ratio of ui plus 1 minus ui over ui minus 1. And do we see why phi should depend on that ratio? Exactly. So if you define this value as, let's just call it r, just ri for short, right? So if r is equal to 1, phi should be 1. If r is negative, phi should be 0. Okay, very good. So we already know two constraints we want. We know that phi should be equal to 1 or 0 if r is equal to 1 and r is less than 0. Or if you draw the diagram of r and phi, right? R can go from minus infinity to infinity. It can be any value, right? It's the ratio. But when r is less than 0, we know that the value of phi, if I use red, should stay at 0, no matter what r is. When r is equal to 1, the value of phi should be equal to 1. All right? So these are two hard constraints of what a limiter should be. Okay? And now let's look at, is there any other constraints of what the limiter can be? Another constraint, as we said, is that the reconstruction cannot exceed the value at the next cell. So that means my reconstruction, which is ui plus half of delta x times the slope of I plus half. That's my reconstruction at I plus half, right? That cannot be, that has to be less or equal to ui plus 1, right? If it exceeds ui plus 1, then, because I have no idea what ui plus 2 is, right? If ui plus 2 is actually lower, that means ui plus 1 is a local maximum, and I cannot just exceed that local maximum. So that cannot be true, which means if I plug the formula of the slope into the definition, so remember the slope is equal to ui minus 1 over delta x times phi of this r, right? Phi of r. Okay, where let me define r as ui plus 1 minus ui divided by ui minus 1. Okay, that has to be less or equal to ui plus 1. And interestingly, if you move ui to the right, that gives us interesting inequality, because now, okay, so the delta x cancel each other. The delta x's cancel each other, so I can just write as ui minus 1 times half of pr has to be less or equal to what? ui plus 1 minus ui. Right? Or phi of r has to be less or equal to 2r. Right? I'm just dividing both sides by ui minus 1. And after the division, the right hand side is exactly r. Right? So that's just the constraint that when I reconstruct from the right, I cannot exceed this local maximum. So on this plot, what does this give us? That gives us, okay, so if phi is equal to, if r is equal to 1, phi cannot equal to 2. Phi cannot exceed 2, right? So it gives us a line like this. And this is forbidden for any valid limiter. Another constraint for a limiter is not this particular use of limiter, but like if you also want the reconstruction, let me go back one slide. Oops. If you also want to use the same slope on the left hand side, on this side of the interval, all right, and you don't want this reconstruction to dip below the left value, what does it put on the, what constraint does that put on the limiter? It means the reconstructed slope cannot be twice as steep as the slope of connecting this center with that center, right? Let me actually draw it. Go back. Pen. So okay. So if you connect this with this center, it is going to be like that. Okay, and the twice as steep is exactly connecting this point with the center. And the other constraint is saying that the slope cannot be more than twice as steep, which means, okay, which means the value of r, the value of phi, that's the other constraint, the value of phi can never be greater than 2. Alright, so that puts a constraint like that. So this is value of 2. That puts a constraint saying that this region is also forbidden. Okay, so that extends all the way to infinity. And then there are other constraints on the limiter, not for the TVD purpose, not for the total variation diminishing purpose, but for the purpose of being a second order scheme, right? So for example, the value of phi has to be equal to 1 when r is equal to 1 is a constraint on being a second order scheme. So if you put all the constraints together, you're gonna get like basically a viable region of the limiter. And the viable region turns out to be something like this. So let's see. So for the second order, I think you can't go below here, and you can't go below here, and what else? And there is also a region you can't go above here, I think. I think you also get a constraint like that, if I'm not mistaken. Right, so I think for the second order purpose, you cannot also dip inside here, right? That basically constrains you to go through this point where when r is equal to 1, phi has to equal to 1. Or when you are in a very smooth region, you have to do a second order extrapolation. Okay, so now I have outlined all the constraints, and the region in between is where the limiter can go. Okay, so that's the region where I can construct a valid limiter functions. So let me